Yeah, don't worry. I know that you were very disappointed to have a week off. Problems, that's last week. But don't worry, you won't be bored this weekend. There is another problem set. Good. Okay. So today what I would like to do is I'd like to continue our discussion of the relationship between scattering amplitudes, so matrix elements, quantum mechanical amplitudes of the sort that we've been computing for the last few weeks. And we've developed a nice set of techniques, the Feynman diagram techniques for computing, and things that we would actually observe, things like decay rates of particles or of cross sections, which are the things that you would actually measure in some sort of particle physics experiment. Okay. So in particular, I'd like to imagine that we have some sort of particle experiment. So let's say we're at the LHC, and we have some sort of beam of particles. And we'd like to ask how we can translate our calculation of the quantum mechanical amplitude for some collection of incoming particles to transition into some collection of outgoing particles into some observable quantity that we would measure at an accelerator. Okay. So first of all, how would we characterize this beam of particles? Well, one way of characterizing the beam of particles is by talking about the flux of particles in this beam. So here, what is the flux of particles? The flux is the number of particles times the velocity that those particles are traveling at. And when we talk about a flux, we usually mean something like a flux per unit volume. So this would be the number of particles per unit volume, so the density of particles times the velocity at which those particles are traveling. And this is really, if you think about it, the number of particles that you see passing through a particular area per unit time. Okay. So in particular, you could imagine some target here, or which has some particular cross-sectional area. And the flux that we're looking at is the number of particles that are incident on that target per unit area of the target per unit time. And the thing that you would actually measure in a particle physics experiment would be the cross-section, typically denoted sigma, and that would be the number of particles scattered by the target or by some collision process divided by the flux per unit time. Okay. So for example, if you have a target and you're throwing particles at it, but the particles don't interact with the target at all, they pass right through, the cross-section would be 0. More generally, if you have some sort of target, you might be interested in studying not just the total cross-section, which I've denoted sigma, but you might be interested in studying what happens to the particles as they're incident on this target as a function of the scattering angle. So for example, you could look not at the total number of particles scattered, but the number of particles scattered as a function of the angle theta, the relative angle at which they're scattered, relative to some axis which you could take, for example, to be the direction of the incident beam. And this cross-section, regarded as a function of the angle theta, is the thing that you would actually measure in some particle physics experiment. If, for example, we were talking about the LHC, and you're scattering not against some hard target, but you're taking two beams traveling in opposite directions, you're colliding them against one another, and you have the collision point with the detector surrounding it, then this cross-section is literally the number of times that your detector goes bing as particles are incident upon the detector. Okay. So when we talk about the cross-section as a function of scattering angle, what we really mean is we're talking about a differential cross-section typically denoted d sigma. And in general, if you just have one particle, you might only care about the single angle theta at which that particle is scattered. But if you have many finals particles, let's say that you have n particles in your final state, then you would look at the differential cross-section as a function of the angles that I've called omega 1 up to omega n at which these final state particles are scattered. So here, omega I is the solid angle into which the ith particle in the final state is scattered. And here I denote by omega the solid angle. So that's really, if you think about spherical coordinates, a collection of two angles, usually denoted theta and phi, that describe the two angles on the sphere, the S2, into which these particles are scattered. In the case of a single particle being scattered, usually we can reduce that just to a single angle theta because you have some rotational invariance. In particular, if you think about this axis of symmetry there, you have a rotational invariance in the axis of symmetry, so the actual cross-section will only be a function of that angle theta. Right? Indeed, when we worked out our 2-to-2 scattering example last class, the only kinematic variable that actually entered into our calculation was a single scattering angle theta. But in general, you'll have these two-dimensional scattering angles, omega 1 up to omega n. And the total cross-section is just the integral of this differential cross-section over all final state angles, d omega 1 up to d omega n. And the basic idea is that if you investigate the dependence of this differential cross-section on these angles, this is some data that really encodes the shape of the target. For example, if you imagine the simple picture that we've drawn up here, where you have some beam of incident particles that's incident on some target, then if the target is a perfect sphere, then you would imagine one particular shape for this differential cross-section, so one particular functional form for d sigma by d theta. But if the target is an oval or a square or something like that, then you would get a different sort of shape. Okay. And so this is clearly some sort of interesting thing that we would like to learn how to extract from our Feynman diagrams. Okay. And the question then is, how do we compute this from one of these S matrix elements that we've spent so much time learning how to compute? So this is what we're now going to describe. Maybe before I go into that, I can pause and see if there are any questions about the basic setup. Great. So rather than work in complete generality, what I'd like to focus on is the typical sort of process that we might be interested in if we have some sort of particle accelerator, which is a process where we have two initial particles. So you're scattering two particles together, such as you would be doing at the LHC, and you have an end state with n final particles. So this is a slight generalization of the 2-to-2 scattering that we discussed last class. Now, the thing that we know how to compute is the S matrix element, Fi, and this is a quantum mechanical amplitude, which means that if you want to get a probability, you should really square it. And so that means the probability of some scattering event is going to be proportional to the square of this S matrix element. So we expect that d sigma should be proportional to the square of this S matrix element. In particular, remember that the initial and final states are characterized by a set of momenta. So for example, your initial state is labeled by 2 momenta that we, I think, called maybe Q1 and Q2 last time, and the final state will be characterized by n momenta, P1 up to Pn. And so if you want to calculate, say, the differential cross-section, then you need to calculate not a total probability, but rather a differential probability that your particles will be scattered into a particular set of final momenta. And what that should be equal to the square of this matrix element times some sort of measure that I'll denote d pi. And this is a measure on the space of final momenta, which we can call pi. I don't remember if I called them pi's or qi's last time, so we'll call them pi's here. So I here runs from 1 up to the total number of particles in the final state. Okay, I guess I call that capital N. And there's one final subtlety that we need to discuss, which will unfortunately be important here, which is that if you remember how we normalized our states when we were talking about free field theory, our 1 particle, 2 particle states, and so forth were not actually unit normalized. There was a normalization factor. So in order to keep track of that, we just have to divide off. We just have to make sure that everything stays unit normalized. Because remember, a probability is only proportional to an overlap. It's equal to the overlap if you normalize your states to be unit normalized. So you have to take care of those factors of the norms of the initial and final states if you want to get the correct probability. So what now is this measure on the space of final momenta? So we have n momenta. So we have to take a product where I goes from 1 up to n of a measure factor of the Lorentz invariant measure factor on these final momenta. And we should really normalize this. So one of the things that is going to be slightly subtle about this calculation is that there's going to be all sorts of infinities floating around over the place, which come from the fact that space has infinite volume and time runs from minus infinity to infinity. And so in order to keep everything finite, what I want to do is I want to imagine that space, instead of being infinite volume, it has some large but finite volume V, and similarly that time runs over some finite interval of length that I'll call capital T. Okay. So all I'm doing here is I'm pretending that instead of space being infinite, I pretend that space is a very large box of volume capital V, and that similarly time only runs for a finite amount of time. So for example, if you want to count, what we're doing here is we're really, well, okay. So this is necessary in order to just keep track of some of the infinities and the delta functions that will appear at intermediate stages in our calculation. Really, it's because, you know, when I define things like a flux and a cross-section, I'm defining them per unit time. I'm defining them per unit volume here. Okay. So when I talk about this measure on the space of final momenta, d pi, what I'm going to do is I'm going to normalize it such that if you integrate over all of the pi's d pi I, you should just get 1. Okay. So what does that mean? That means that I should really put a volume factor here, because d3p has units of 1 over length squared, so it is units of 1 over volume. So by putting a factor of volume here, I'm really just ensuring that the integral over all final state momenta is equal to 1. So that's just a way of keeping everything nice and normalized. So another way of saying that is that if I just had a naive integral over one of these final state momenta there, so if I integrated over all space, I would get something proportional to the volume of space. And if you integrate over all momenta, just by dimensional analysis, that has to go like 1 over volume. It's a slightly subtle argument, but yeah. Right. Any questions on this so far? So far I haven't really done anything except interpret this scattering amplitude here as something that you square in order to get the probability for some scattering event. And I've written down the differential probability as a function of the final state momenta, and I've normalized everything appropriately. Yes?
What do you need the time interval to be finite?
We'll see in just a second. Okay. The reason really why we need the time interval to be finite is that when we write down the differential cross-section, so what is that? So the cross-section was the total number of particles scattered. So we now want to take the differential of the number of particles scattered per unit flux times time. And if I don't take that time interval to be finite, then I am dividing by infinity here, so I would just get 0. So what is this? So this is dp over flux times time, where what is the flux? Remember, the flux, just referring up to here, flux was the number of particles times velocity per unit volume. So if, for example, you're working in center of mass frame, this is the velocity at which two particles are colliding with each other divided by volume. So that would be in center of mass frame. Or, more generally, if you're not in center of mass frame, it would be the difference. Remember, we have two incident particles. It would be the difference V1 minus V2 divided by the total volume. I mean, I should probably make one comment here, which is that really when I talk about the cross-section, I'm talking about a number of particles scattered, and when I talk about a flux, I have a total number of particles times velocity per unit volume. But I'm really thinking here about a single particle, and what is the flux associated with, or a single set of two incident particles. So if you have two incident particles in center of mass frame, what is the flux associated with that? Well, remember, the flux was the number of particles times velocity per unit volume. And we have a single set of incoming particles here, so the flux is just velocity per unit volume. And similarly here, you're really thinking about a single particle undergoing, or a single set of two particles undergoing some scattering process. And so that's why we get just the differential of that probability there. The probability that a single set of two particles will undergo some scattering event. Of course, you could take n particles instead of one particle, but then you would get an n in the numerator that would cancel out some n in the denominator. Sorry, that n is not the same capital N that I used above, which would denote the number of particles in the final state. But here I'm considering n sets of two incident particles, and then the flux would get multiplied by n, and then the probability of a scattering event would get multiplied by n as well. The nice thing about a cross-section is that it's something that you consider where the n's factor out. You know, it doesn't depend on how many times you do the scattering event, the scattering experiment. And so this expression here, is just in center of mass frame, where you have two particles that are incident. You know, one with velocity plus v and one with velocity minus v, if you're in the center of mass frame. And then you can go to some other frame where the particles would have some different velocities, and you would get something like v1 minus v2. So here, this is where the initial particles have velocities v1 and v2. Okay. I should make one note here, which is that I'm actually not going to be very careful about factors of order 1. So in this calculation of the cross-section, there are various factors of 2 and pi and stuff like that that will appear along the way. Just to make life simple, so for this calculation, I'm going to neglect factors of order 1. Just because there'll be too many factors of 2 and pi floating around for me to get the exact correct answer, so I'm not even going to try. If you want the exact correct answer, you can look it up in the textbook, for example. Good. Okay, so we're computing the scattering cross-section. We have the differential probability. We wrote it down up here. We have the flux. All we need to do now is we need to compute these quantities that are appearing in the denominator, the norms of the initial and final states. Okay. So I want you to remember back to our discussion of free field theory. And I want you to remember that we actually normalized our states in a somewhat funny way. So a state, for example, a single particle state describing a particle of momentum k was given by a factor of 1 over the square root of energy times the associated raising operator acting on the vacuum state. So that means, for example, that the inner product between two states is given by a delta function that sets k1 equals to k2, right? But with a normalization factor. That's the energy of the state. So that the norm of a single particle state of momentum k, well, you get a factor of the energy of the particle, so we'll call that E. Maybe I'll call it E sub k. I'll just call it E. Along with a delta function of 0. But that delta function of 0, that's infinity, but what is that infinity? That infinity is the volume of space. Okay. An easy way to see that is just to note that what does a delta function do for a living? A delta function, what it does is you integrate a delta function to get 1. Okay? And if the integral d3p is equal to 1 over v, then that means that the delta function in momentum space has to be proportional to volume. Okay? So that's something, if that's unfamiliar to you, you can really just use this, use dimensional analysis to make these sorts of arguments, right? The statement is that the integral dx of delta of x is equal to 1. Okay. So what does that mean? That means that the dimension of delta of x is 1 over the dimension of x. So if x has dimensions of length, then the delta function has dimensions of 1 over length. So a delta function of momentum has dimensions of 1 over momentum, which is length. And so a three-dimensional delta function, a delta function of 3 momenta has dimensions of volume. So that, for example, what does this mean? This means that for a two-particle initial state, of particles with energies E1 and E2, what is the norm of the initial state? Well, you get two factors of this normalization factor, so you get an E1 times V and an E2 times V. And similarly, for an n-particle final state, of particles with energies EI, the norm of the final state is the product over all I of V times EI. Okay? So those are what the norms are. And finally, in order to calculate this cross-section, so we need to compute this numerator here, so the S matrix element. And what was that S matrix element? So the scattering, so the square of this S matrix element what is that? Well, that was the norm of this transition probability. So this is the thing that we worked so hard to compute using Feynman diagrams. And remember, we characterized that we usually, when we compute this S matrix element that we called M, we pull out a factor of a momentum conserving delta function. So I guess. So if the initial states have momenta Q and the final states have momentum P, then we pull out a factor of that momentum conserving delta function, and the remainder is the thing that we called M, and M is the thing that we compute using our Feynman rules. So M is the S matrix element. So this is the thing that we compute using Feynman diagrams. So here, this is the sum over the initial states minus the sum over the final states. So what I'd like to do here is I just want to, we have the slightly confusing situation where we have a square of two delta functions. Okay, so you get two copies of this delta function. We have the sum of the initial momenta minus the final momenta. And of course, the first delta function sets the initial momenta equal to the final momenta. So you should really think of this as a four-dimensional delta function of 0 times the square of this scattering amplitude. But what is this four-dimensional delta function of 0? Well, again, by dimensional analysis, the argument of the delta function was a 4 momentum. And a delta function has dimensions of 1 over its argument. So this has dimensions of volume times time. And indeed, if we regulated our theory by putting it at finite volume and for finite time, that'll be V times T. So we can now go ahead and put this all together. Okay, so what was d sigma? The differential cross-section was the probability dp divided by the flux times time. Okay, let's see if I got all of my factors right. I'll be very impressed if I did. Okay, let's give it a try. So what was that flux? The flux was given by the difference in the velocities over volume. So you get velocity over differences So if you have two incoming particles, then the flux is the total volume divided by the difference in the velocities of the particles. We have a 1 over time. And what was dP? Well, in the numerator you had this transition probability. What is that transition probability? Well, you get Vt times this matrix element M times a momentum conserving delta function, so sum of Qi minus the sum of Pi's. Then we had to divide out by these normalization factors, so the norms of, where was it? The norms of the initial and final states, which we computed here. So for the initial state, we have a two-particle state, so we have the energies E1 times volume and E2 times volume of the two initial states. And then we have a normalization factor for each one of these final states. So volume times energy for each final state. And then finally we had the normalization factor, we had the measure on the space of final momenta. Okay. So a product over I going from 1 up to n of volume times d3 pi. Okay. Good. So let's see if I did this correctly. So if I did this correctly, our answer shouldn't depend on the values of v and t. I should be able to take v and t to infinity without running into any problems. And so let's see, in the numerator, I have n factors of v here that cancel n factors of v here. I have 2 factors of v here that cancel 2 factors of v down here. I have a time here, which cancels a time here. So at the end of the day, we can now take away those cutoffs v and t to get an expression for the total differential cross-section. What is that expression? So the differential cross-section is given by the square of our matrix element, and then we have a prefactor which depends on the energies of the particles in the initial state, E1 times E2, and the difference in the velocities of the particles in the initial state, times this momentum conserving delta function, so which says that the initial particles and the final particles have the same total momentum, momentum, along with these measure factors associated with the final state particles. The product of I going from 1 up to n, d3pi over EI. So this is really the final expression for the scattering amplitude. I want to just take a few minutes for the differential cross-section. I thought I should take just a few minutes to make some comments about this expression. So the first thing to notice is that, of course, it's proportional to the square of the matrix element, as we would anticipate. One comment that I'll make is that this means that, as always, when we study quantum mechanics, you have a wave function, or an amplitude, which is complex, and a probability, or in this case a cross-section, which is a real number that's formed by taking the absolute value squared. But as always in quantum mechanics, you can get interference effects, where if your wave function is complex, you can get either destructive or constructive interference. And similarly in quantum field theory, if you have Feynman diagrams, you can get constructive or destructive interference between different terms in these matrix elements. It turns out there's a sort of beautiful theory about when Feynman diagrams will and will not interfere constructively or destructively with one another. It's not something that I really am going to focus on in this course, but I just thought I would make a comment that just as always when we construct an observable from a quantum theory, but when you're taking a square of a wave function, and so you can get interference effects, and you can get interference effects in scattering amplitudes as well. The second comment that I'll make is that this measure factor is actually Lorentz invariant. In particular, this momentum-conserving delta function is a four-dimensional delta function, so it's Lorentz invariant. And moreover, hopefully you remember, because you did a problem on it earlier on in the course, that the correct Lorentz invariant measure factor in an integral, you could either do an integral d4p, or you could do an integral d3p over the energy. I assigned that as a problem, right? I think I assigned that as a problem. So that this measure factor here is Lorentz invariant as well. So sometimes people give a name to that Lorentz invariant measure factor. They call it the Lorentz invariant measure factor. Okay. So Lorentz, or the Lorentz, or I guess sometimes call it the Lorentz invariant phase space factor. So sometimes you'll see that notation, d pi LIPS, standing for Lorentz invariant phase space. And this is the Lorentz invariant phase space factor, or the Lorentz invariant measure factor on the phase space, or the momentum space, of outgoing particles. But it's really this quantity here that I think it's worth thinking about for a second. The point is that this quantity here is not Lorentz invariant. And the reason why this is not Lorentz invariant is that the definition of the differential cross-section itself, or the definition of the cross-section, is not a Lorentz invariant quantity. So for example, you could, if you have a beam of particles at some velocity, you could always go to the rest frame of that beam where there's no scattering whatsoever. Okay. Or you could imagine going to a frame where you're moving in a transverse direction with some relative velocity, in which case there would be some length contraction effects that would affect the size of some target that you're scattering off of. And so the fact that this factor that we're getting here depends on things like energies and velocities is a signature of the fact that the cross-section itself is a frame-dependent quantity. So typically, for something like 2-to-2 scattering, we will study this in the rest frame. And I thought it might just be instructive to work out explicitly what this is for two-particle to two-particle scattering in the rest frame. Okay. So in particular, let's just focus on 2-to-2 scattering. Okay. So here, in this case, oh, well, maybe before I do that, I should pause and see if there are any questions. Yes?
In that scattering cross-section, the V1 minus V2 term seems to imply that the scattering cross-section will blow up if the particles are moving exactly the velocity.
Yeah. So that's right. I mean, it's sort of because the two particles will then be on top of each other for all time. Because remember, the scattering cross-section, yeah. I mean, that's exactly right. So what you're doing is you're imagining that this is some cross-section for two particles that are coming at each other from, in center of mass frame, they would be coming at each other from equal and opposite directions at equal and opposite velocities. And so the scattering will happen once, and you'll count the number of events that happens. if you tried to go to a frame where both of the particles have equal velocity, well, first of all, you can't really do that. You can't actually go to such a frame. You could try and do a very large boost so that V1 is very close to V2. And if you do that, you will get a very large answer. The reason being that those two particles are very close to each other and will interact for a very, very long time. You know, you might hope that in such a case E1 and E2 would go to 0 in such a way to cancel out that effect. But that is in fact not what happens. If you go to a frame where the particles have have V1 very close to V2, you're moving with a very large relative velocity, so E1 and E2 are very, very large. Okay? But I don't think, actually, no, I take that back. Maybe they are large enough to cancel it out. Okay, exercise. For you, because you asked the question, actually study what happens when you go to a frame that's moving with a very, very large velocity. I actually have a guess for what I think will happen, which is, I actually think that, actually I'm not sure what will happen. Okay, good question. Right, good question is what you say when you don't know what the answer is. Good, excellent question. Good, okay. Any other good questions? Well, the simple answer to your question is that you can't actually go to a frame where they have the same velocity. But then I managed to turn that into a more complicated question I didn't know the answer to. Okay, good. So let's imagine we have 2-to-2 scattering. So your final state is characterized by two momenta, P1 and P2. And in center of mass frame, sorry, I should have said center of mass, rest frame. So in the rest frame of the center of mass, P1 is equal to minus P2. So the particles are coming in to scatter at equal and opposite velocities. And so and similarly, the initial states are coming in at equal and opposite velocities. So similarly, the initial state, I guess what we called Q1 and Q2, will have equal and opposite velocities. And the energies of all of these particles, so for example, the energy of that first incident particle is Q1 squared plus m squared, is going to be equal to E2, which is Q2 squared plus m squared, or the square root of Q2 squared plus m squared, which is 1/2 of the total center of mass energy. The particles come in with equal and opposite velocities and equal energies. I guess here I'm assuming that the particles have equal mass. Okay. So for example here, I think in the problems that I just handed out, you're going to be doing an example where they don't have equal mass. So what does this phase space factor look like? So the phase space factor what is it? Well, there was this Lorentz invariant phase space factor for the final state particles. So what was it? It's d3p1 times d3p2 over E1 times E2 times the momentum conserving delta function, which sets, well, what does that momentum conserving delta function do? It sets P1, well, it sets the total for momentum P1 plus P2 equal to Q1 plus Q2. But what is that momentum conserving delta function? Well, first of all, it's a delta function in three-dimensional space for the momentum vectors that sets P1 vector equals to P2 vector times an energy conserving times a energy conserving delta function, which, if you like, you can think of as setting E1 plus E2 equal to the total center of mass energy. So we can then use this momentum conserving delta function to do one of those momentum integrals. So really, this phase space variable is going to be integrated. Right? So eventually, if you want to compute the total amount of scattering into some finite region in momentum space, some finite solid angle, you'll have to integrate this. And so you can do the P2 integral just using that momentum conserving delta function. And what will you get? Well, you'll get a d3p1, which you could write as p1 squared dp1 times d omega 1, where d omega 1 is the solid angle into which the particle p1 is scattered, and p1 is the length of the vector. So p1 is the length of the vector p1. So then you have divided by E1 times E2. But of course, E1 is equal to E2, and both of those are equal to the total center of mass energy, up to some factor of 2 that I'm not really keeping track of here. Times this delta function in energy space, times a delta function, which sets the energy of the first particle equal to the total center of mass energy. Okay? So it's a delta function that sets the total E1, which is equal to P1 squared plus m squared, equal to 1/2 of the total center of mass energy. And now I can use this delta function here. So why did I call it? That's just a delta function, not a delta zero. I'm not quite sure why I called it delta zero. We can use that delta function to do the P1 integral. It's actually a little bit subtle to do that. Okay. So the way that you want to think about doing this is you actually, because this is not a delta function of P1, but a delta function of the square root of P1 squared plus m squared. So you actually need to do a change of variables in order to get all of the factors correctly. So in particular, what I want to do is I want to do a change of variables, where I want to set, I want to go from the P1 variable to the E1 variable. Okay. So there's a Jacobian determinant, a Jacobian associated with that change of variables. So in particular, I want to think of, instead of doing an integral of dp1, but an integral of dE1. And so we have a P1 dP1 is equal to E1 dE1, so that this Lorentz invariant phase space factor becomes P1. So here, I guess in this denominator here, I called that E center of mass, but of course that's the same as E1 up to some factor of 2. So just to keep everything clear, I'll call that E1. So you get P1 over E1 times this delta function, 2E1 minus E dE1, times this solid angle d omega. And then you can use the energy conserving delta function to do the integral over the energies. And so this Lorentz invariant phase space factor is just P1 over E. Good. Up to some factors of 2 that I'm careful to neglect. So what does this mean? This means that the differential cross-section, so let's just put that all together. That's 1 over, well, we had an E1 times E2, where E1 and E2 were now the energies of the initial particles rather than the final particles. But these all have the same energy, okay, which is, we're just denoting E. It's half of the center of mass energy. So we'll just call that E center of mass squared. Then we have the V1 minus V2, which was just V in the center of mass frame for the initial particles. And then we have a P1 over E times the matrix element squared. And in fact, we can simplify this a little bit more by noticing that, of course, momentum is proportional to velocity. And in fact, you just need to remember your relativistic kinematics. So what is the relationship between momentum and velocity? Well, momentum in non-relativistic theories is mass times velocity. And in relativistic theories, you need this relativistic gamma factor. And there's another name for the quantity gamma m. What is it? Anyone know? If particles are not moving, it's just equal to m, otherwise known as mc squared. If particles are moving, it's bigger than that. It's, of course, just the same as the energy of the particle, okay? Since in relativity, right, in relativity, E is equal to the square root of p squared plus m squared, otherwise known as m times the relativistic gamma factor. So, in fact, this E times V in the denominator cancels the P, and what you get is that the total cross-section to scatter into a particular angle is the matrix element squared divided by the center of mass energy squared. And there's some numerical factor that I haven't kept track of, because if I tried, I certainly wouldn't have gotten the 64 pi squared correct. But you could, for example, look in the textbook, and it's all derived in gory detail. So, for example, you're now in a position to take the answer that we derived last time for the 2-to-2 scattering matrix element in phi cubed theory, and go ahead and compute some sort of experimental observable, namely the probability for your particles to scatter into a particular angle theta. And in fact, that's what you're going to do on the first problem in the problem set I just handed out. Good. Excuse me. Any questions before I continue? Yes.
So, diffuse space, I didn't quite understand how do you go from the delta 4 to delta T1 or T2?
Good.
Yeah, yeah.
So what is this?
T1 plus T2, isn't it just 0?
Yes, that's what the delta function does, is it sets P1 equals to P2.
Okay. And how do you get to
So let's put it this way. In this relativistic, when I wrote down this phase factor, I'm doing an integral d3 P1 and an integral d3 P2. And I haven't yet set P1 equals to P2 when I do that. That delta function is the thing that sets P1 equals to P2, or minus P2.
Okay.
Right? Because why, let's put it this way. We work in the center of mass frame for the initial particles, which means that Q initial, that the initial particles have a total momentum equal to 0. And so, and similarly, And so that means that the momentum conserving delta function here is, well, it has a spatial part which sets P1 plus P2 equal to the initial total momentum, which is equal to 0, which is this factor that I wrote down here.
So you,
Yeah. So remember, this Lorentz invariant phase space measure is just this phase space measure here times the delta function that enforces momentum conservation. Good. Good question. Sorry if that wasn't clear. And similarly, this factor here is the thing that enforces energy conservation.
it's kind of redundant in the center mass.
Yeah, I mean, in the center of mass frame, it's all very simple. So I went through it a little more quickly than I should have, maybe. But that's right. Yeah. Good. Any other questions? I hope that was more or less clear. I'm not doing anything aside from sort of basic relativistic kinematics here. You know, all of the really hard calculations that we do in this class are going to involve calculations of these matrix elements. Going from there to scattering amplitudes is some completely, in principle, straightforward relativistic kinematics. Although today, you know, I had to be very careful about regularizing things and delta functions and stuff like that. But there's nothing here that's fancy. Right? It's just sort of special relativity kinematics. Good. So, of course, so far we studied only 2 to n particles, 2 to n particle scattering. But one could, of course, study other sorts of processes, 3 particles, 4 particles, and so forth. The other very natural process that one could study is 1 particle to n particle scattering, otherwise known as the decay of a single particle into n products. You know, most of the particles that one might produce at an accelerator, for example, are not stable particles. They're unstable particles, and they'll decay. And one of the things that we might want to study is the lifetime of the particle, or you know, the various properties of the decay process. So just as when we're studying 2 particle scattering, it's natural to talk about a cross-section, the analogous quantity when we talk about a decay process is the decay rate, typically denoted gamma. And if we have some collection of n particles, this is defined as the number of particles that decay divided by the total number of particles per unit time. And just as with the differential cross-sections, it's natural not to talk about a total decay rate, but to study a more refined quantity, which would be the differential decay rate, d gamma, which describes the relative probability that your particles will decay that a single particle will decay into n products that have some configuration of final momenta and energies. So this is going to be similarly proportional to dp, where p is the probability which we evaluate per unit time of a decay into n particles with some particular final momenta. That we could call pi. And we could go ahead and we could repeat the argument that I just gave above, where we evaluate all of this explicitly in terms of the initial and final states. And if you do, you're going to get an expression which is very similar to this expression that I wrote down up here. In fact, it's going to be essentially identical to the expression that I wrote here, except I just have to remove all of the pieces of this equation that refer to the fact that I have two initial particles instead of one initial particle. In particular, you just need to remove this factor here and this factor here, because now there's no relative velocity. Okay. There's just one single initial velocity, and there's only one factor of an energy. So if you go through the argument is nearly identical. You'll see that in center of mass frame, the decay rate, or the differential decay rate, is just given again by a matrix element, now one particle to n particle matrix element, times a Lorentz invariant phase space factor, divided by the energy of your initial particle, which of course is just the mass of the particle if you're in its rest frame. So you're now in a position to go ahead and compute all sorts of interesting observable quantities. So, for example, let's imagine that we have two fields which are coupled by some interaction term which allows a chi particle to turn into a pair of phi particles. Then what you would see, so what sort of processes would you expect could arise because of this interaction term? Well, you'll have a decay. So, for example, the chi particle will be able to decay into a pair of phi particles. And without even going through any of the details, you can immediately see that the decay rate of the chi particle is going to be proportional to the coupling squared coming from Feynman diagrams like that, where you have one chi particle that splits into two phi particles. Here, say, we're assuming that the mass of the chi particle is large compared to the mass of the phi particle. Otherwise, the decay of the chi particle into the phi particle would be kinematically forbidden. So you would never be able to enforce momentum conservation or energy momentum conservation and have a chi particle decay into two phi particles unless the chi particle is heavy compared to the phi particles, in which case you would have this decay process where the decay rate would be proportional to the coupling squared. And similarly, the scattering cross-section of two phis into two phis will be proportional to coupling to the fourth, coming from the square of a diagram that looks like this, where you have some scattering of two phis off of each other by the exchange of a chi particle. And so if we wanted to, and I hope you want to because you will, on your problem set, if we wanted to, we could then go ahead and include all of the various energy-dependent factors that will appear when you include, first of all, the various factors that would arise from the computation of this Feynman diagram, as well as all of the energy-dependent factors that would arise from these phase space measure factors that we just derived above. So for example, on the problem set I just handed out, I believe you're going to calculate this guy exactly, including all of the various factors. It's not very hard. And then a slightly more difficult problem is to go ahead and calculate this differential cross-section here. In particular, what you'll need to do is you'll need to square the answer that we described last class in terms of the Mandelstam variables for this 2 to 2 scattering. So actually, I suppose I lied here. I should say plus 2 other diagrams, right? Because there was S channel, T channel, and U channel scattering. You'll sum them all together. You'll get an answer that's a function of energy. So in center of mass frame, for example, it'll be a function of the center of mass energy as well as the scattering angle. And you'll go ahead and compute explicitly what that scattering cross-section is as a function of that energy and scattering angle. Okay. So that's just about all I wanted to say this class. Maybe I should, we have a few, I ended a little bit early, so maybe I should just, well, maybe I'll pause and see if there are any more questions. Yes?
What is the M-chi squared that should be like much bigger than size?
Well, that's, when you do problem 3 on the problem set, you'll understand exactly how much more massive chi has to be than phi.
Like I understand there has to be like enough energy for this, but then like why do this the particles like phi has to like be fast or something?
Maybe, I'm not quite sure.
Because,
Right.
like if
Let's
there's
put it
a-
this way: if m phi is m chi is equal to m phi, then the chi particle at rest will not have enough energy to decay into phi
Yeah,
particles.
it's true.
You know?
Like if it's just has enough energy to decay into like two particles at rest,
Mhm.
that's not gonna be
What's that?
like it's allowed.
Yes, that's right. That's right. So when I only said much greater rather than including that factor of 2, because that factor of 2 is one of the things that you're supposed to conclude on your problem set. Okay.
Because if
It's
they're
kind of
much
easy.
bigger,
Okay,
I-
fine. I ruined the surprise. But yes. Okay. Fine. You win.
I just imagine that.
Okay, good. Yes,
Well,
fine.
it's
2.
bigger.
Okay. Ruined the surprise for everyone. Yes. Okay. I mean, yes. As you say, that's very sort of straightforward conservation of energy. Okay. Yeah. Indeed, as you can see, the total velocity of the final phi particles is going to be determined by m chi squared minus m phi squared, or minus 2m phi squared. Good. Other questions? Okay. I mean, so at this point in the course, you now have all the tools that you need to calculate anything in quantum field theory. All it is a matter of putting everything together. Okay. We've learned the Feynman rules for calculating matrix elements. We've learned how these matrix elements translate into physically observable quantities. All that we need to do now is understand how to use these Feynman rules for theories of physics that we're interested in. So, for example, the only thing that's slightly subtle that we haven't discussed yet is that the theories of physics that we're most interested in are theories not of scalar fields, usually, but theories involving fermions and vectors. And the derivation of the Feynman rules that we gave follows almost without modification for theories of vectors and fermions. In particular, say, for example, for QED, rather than for a free scalar field, we have a gauge field, or an electromagnetic field, phi, and a spinor field describing the electron and positron, psi, and the scattering amplitudes are going to be computed just using the exact same Feynman rules that we developed earlier, except that now we need to keep track of the fact that the electromagnetic field now has an index mu, indicating that it's a 4 vector, and the spinor also, it has an index, one that we don't usually like to write down, but has an index representing the fact that it's a collective field that's 4 separate functions of space-time. So, for example, there'll be a propagator for your photon, which is something that we've already computed. Okay. This is what we call the Feynman propagator, or the propagator and Feynman gauge for the photon. And similarly, from the action, there was there'll be a propagator for the electron, okay, which is something that we also calculated in momentum space. And finally, there'll be an interaction term, which encodes the fact that your electrons and positrons carry charge. And what was the interaction term in the Lagrangian? Remember that in the Lagrangian, the interaction term was something like E times A mu psi bar gamma mu psi. So this interaction term will be I E times gamma mu. So rather than trying to give a complete discussion of the Feynman rules of quantum electrodynamics here, next week I'm going to give you a slightly more systematic derivation of these Feynman rules. But hopefully, given all of the time that we've spent deriving the Feynman rules for scalar field theories, you can see that it's going to follow in a more or less straightforward manner how we derive these Feynman rules for more complicated theories where you have spinor and vector fields. Maybe I can ask, so I hadn't decided how much time to spend next week. So what I don't want to do, we've already spent a lot of time deriving Feynman rules in scalar field theories. What I don't want to do is just repeat that derivation because it would be almost identical for spinor and vector theories. There are a couple of important distinctions that we will have to go through and understand. But maybe in order to help me decide how much time I want to spend on that, is the fact, given what you've already learned about Feynman rules in scalar field theories, is the fact that these are the Feynman rules in quantum electrodynamics more or less clear? Right. I mean, because, we spent some time deriving the propagator in momentum space, both of the scalar and both of the vector field A mu and the spinor field psi. So hopefully it should all be more or less clear. I mean, there are one or two subtleties that are completely not obvious about how you do Feynman diagrams with fermions as opposed to bosons. So I will unfortunately have to talk about that. But what I probably won't do is repeat completely the derivation of the Feynman rules from first principles for vectors and spinors. Instead, maybe starting next time, what I'll do is I'll just start by stating again very clearly and carefully what the Feynman rules are for quantum electrodynamics before spending some time focusing on the new features that arise for QED as opposed to scalar field theory. But it's sort of exciting. At this point, you've completely understood how to derive the Feynman rules for quantum electrodynamics. In principle, I could hand you a theory, as I will in problem 2 of the problem set that I just handed out. I could hand you a new theory with a new set of interaction terms, and you should be able to figure out what the Feynman rules are from that. Good. So I ended a couple minutes early. Maybe this is a good time to pause and see if there are any questions. Yes?
So regarding the decay unit
Yes.
and its Calvin cross-section, what would happen if we look at the inverse process? Would the amplitude be the same? Or
Absolutely. Yeah, I mean, absolutely. Like there's, there's also a process where two phis can come in to make a chi particle. Okay. You have the Lorentz invariant phase space measure factors will be different, right?
So the decay would be...
Well, maybe I don't quite understand your question. Like, just as a chi can decay into two phis can come in and scatter and produce a chi particle.
Right, and they can do this with a certain decay rate, right?
Well, you would call it a cross section rather than a decay rate, right?
Okay.
Right. But yes, they do it with a certain probability. And indeed, if you looked at this, how did this process where phi goes to phi proceed? It proceeded by, in the S channel at least, these two phi particles colliding to make a chi particle, and then that chi particle decaying to make two phi particles. So, for example, if you put a detector in right here, you would have observed that intermediate chi particle. And in fact, I mean, maybe this is not, there are relationships But, the fact that, there are relationships between this kind of Feynman diagram and this kind of Feynman diagram. But there's a sort of famous theorem in quantum field theory that allows you to relate different Feynman diagrams of these sorts, called the optical theorem, which is actually probably not something that we'll go into. But yes, so, one comment I'll make is that if a decay process is possible, the reverse process is also possible. That's kind of a fundamental principle of quantum mechanics, right? In quantum mechanics, time evolution is unitary, so every process is reversible. Okay. And so it is possible to have two phi's coming in to make a chi. Okay. But to some sense, let's put it this way. Maybe what you're getting at is that it's very easy for a chi particle to decay into phi particles if it's very heavy, right? A chi particle is unstable. So, well, there's a couple of things that we should probably discuss, which is that because the chi particle is unstable, you can't really talk about a chi particle as a final state in the theory. Right? This is actually a kind of important and subtle point, which I haven't talked about yet. Because if you think about this theory, where m chi squared is bigger than 2m phi squared, then you can't have, the chi particle is not a stable state in the theory. This really comes back to the fact that interacting quantum field theory is very different from free field theory. In free field theory, the chi particle had some mass, but the Hamiltonian was a bunch of harmonic oscillators, and we constructed the Fock space describing the chi particle state, and that was it. Okay. And this was an eigenstate of the Hamiltonian. You could take a chi particle with some momentum, and then it would just be some eigenstate of the Hamiltonian, and it would stay there forever. But the fact that you have a process like this means that that state is not an eigenstate of the Hamiltonian. If the mass of the chi particle were less than 2m phi, then you would still have something that looks like a stable chi state. Okay? Because of this interaction term, the state might not look very much like the state that it looks like in free field theory, but you would still have some state describing a stable chi particle. But if the mass of the chi particle is sufficiently large, and it's allowed to decay into other things, there's just no asymptotic state like this. So in particular, if you tried to do some process of the sort that you describe, where you take two phi particles and you scatter them together to make a chi particle, eventually what will happen is that chi particle will decay into two phi's. This is what actually happens, like at the LHC. You create a Higgs, or you create a muon, for example. Eventually, that muon will decay. It might take a very long time, but it will decay eventually. So that means that when you study unstable particles, you really shouldn't talk about these as allowed asymptotic states in your S matrix. Yes?
But even these two phi particles are not a stable state.
Oh, the phi particles are stable because kinematically a phi state can't decay into. So this interaction term, you might think it would allow one phi to decay into a phi and a chi, or another way of saying that is you might think it would allow a phi to emit a chi particle, but that doesn't prevent the phi state from being a phi particle. What it does is it changes the properties of that phi particle. So in particular, one of the things it does is it will change the effective mass of the phi particle. This is something that we will study in great detail. So for example, what it means, roughly speaking, is that every time you think you have a phi particle, it's surrounded by a quantum mechanical cloud of chi particles, which make it which change the mass slightly. Good question.
So are you basically saying that there's basically all of the phi particles phase space allows for decay to phi particles?
Yes.
There's only a small portion of phi particles that allows it to turn into phi particles?
Well, there is a portion of the phi particle phase space that allows it to turn into a chi particle, but really in terms, let's put it this way. There's some Lagrangian here with this coupling, okay? And that means there's some Hamiltonian. And we could talk about what the eigenstates of the Hamiltonian are. Those would be states describing particles that would last forever. And there's no eigenstate that looks like a chi particle, but there is an eigenstate that looks like a phi particle. So that doesn't mean that there aren't chi particles in the following sense. Chi particles don't exist as completely stable objects that are eigenstates of the Hamiltonian, but they could be very long-lived states. Okay? So we would call these a resonance or a bound state or something like that. And so they can exist as intermediate states. I mean, every particle, if you look at the particle data, there's only a handful of actual particles that we know of that appear to be stable. But for some reason, people, you look at the particle data book and it's about that thick, okay? What's it full of? It's full of all of these unstable states, right? I mean, it's full of all of these states which you can't really think of as asymptotic states, because if you create one of them, they'll eventually decay. But they still appear as intermediate states in scattering processes. I mean, a muon is a perfect example, right? They're actually relatively long-lived. They last, in rest frame, I think, microseconds, millisecond. I don't actually remember. You probably had to do this. Is it milliseconds? Yeah. They last a very long time. Okay. By the standards of particle physics, that's an incredibly long time. So you can think of them as approximate asymptotic states to a very, very good approximation. From the point of view of the LHC, they live forever, right? Because the LHC is doing experiments on timescales that are vastly smaller, vastly shorter than that. But from the point of view of someone in this, infinity, from the point of view of some observer in the far past at future infinity, there are no muons. Right? There's no such thing as a muon. Okay? I mean, all of this is just to say that the intuition that we get from free field theory, can only be taken so far, and that in an interacting field theory, the definition of exactly what you mean by a particle is a bit more subtle. The chi particle doesn't exist as an asymptotic state. Okay? You might ask then, if you took this diagram here and you interpreted it as a contribution to a process where two phi's come in and make a chi. I mean, I told you how to compute that Feynman diagram. I told you its value. I said it was I times G. Okay. And I told you what the phase space factor was, and so you could calculate that cross-section. But the point is, you really can't interpret that cross-section physically as an amplitude to create a chi particle. It would really be an amplitude to create a chi particle, which is then, going to subsequently decay into something else. Okay. Good. Okay. I've talked long enough. See you next week.